Picture the universe as an endless treasure chest, filled with cosmic wonders we're only beginning to crack open. Every time we peer deeper into the void, space throws us another curveball, something bizarre, beautiful, or downright inexplicable. Just when we think we've got it all figured out, the cosmos winks back with phenomena that rewrite the rules. And right now, astronomers are uncovering mysteries at a breakneck pace, like children stumbling upon hidden compartments in that celestial chest. Today, we're diving into 25 of the most mind-bending space discoveries that'll make you question everything you thought you knew about the great beyond. Think about this. For centuries, we believed black holes were the ultimate cosmic vacuum cleaners, sucking in everything without a trace. But what if I told you scientists just spotted one belching out stardust like a toddler with a mouthful of crumbs? Or that there's a planet so dark it absorbs 99% of light, yet somehow glows like a ghostly ember? These aren't plot twists from a sci-fi novel, they're real, documented head-scratchers that have researchers buzzing. And the wildest part, each discovery peels back another layer, revealing how little we truly understand about the universe's grand design. This journey isn't just for astrophysicists, it's for anyone who's ever stared at the night sky and felt that itch of wonder. Maybe you've wondered if we're alone or what lurks in the voids between galaxies. Well, buckle up. From stars that shouldn't exist to invisible walls defying gravity itself, we're about to tour the cosmos's weirdest, most awe-inspiring secrets. And trust me, by the end, you'll see space not as a cold, empty expanse, but as a living, breathing enigma, constantly daring us to dig deeper, ready to have your mind blown. Let's go. Imagine tuning an old radio and suddenly stumbling upon a signal so vast it dwarfs entire galaxies. That's exactly what astronomers did when they discovered odd radio circles, or enormous, ghostly rings of radio waves stretching millions of light-years across with no obvious source. These cosmic halos are so colossal they could swallow our Milky Way whole, yet they're nearly invisible in other wavelengths of light. It's like spotting the outline of a phantom in the dark, one that leaves no footprints. When researchers first spotted these eerie circles in telescope data, the confusion was instant. Some thought it might be a glitch, a trick of the instruments, but as more ORCs emerged, the mystery deepened. One leading theory suggests they're shockwaves from cataclysmic events, like the explosive collision of supermassive black holes. Picture two giants clashing in the void, sending ripples through space-time so violent they etch themselves into the fabric of the universe. Others speculate these rings could be the aftermath of a starburst so intense it blasted gas and particles outward in a perfect sphere, like a cosmic bomb frozen mid-explosion. But here's where it gets wilder. A handful of scientists have floated an even more provocative idea. What if ORCs are the fingerprints of advanced alien civilizations? The idea isn't as outlandish as it sounds. A Type 3 civilization on the Kardashev scale, one capable of harnessing the energy of an entire galaxy, might build megastructures or energy beacons that appear as unnatural rings to our telescopes. While there's no solid evidence for this, the mere possibility sends shivers down the spine. What makes ORCs truly humbling is how they defy classification. They're not supernova remnants, not galaxy clusters, not anything we've seen before. They're cosmic Rorschach tests, inviting us to project our wildest theories onto their enigmatic shapes. And as telescopes grow more powerful, one thing's certain: these ghostly circles are just the beginning. Every new detection peels back another layer, reminding us that the universe is far stranger, far more inventive than we ever dared to dream. Now picture this: a supermassive black hole, the kind that usually sits like a king at the center of a galaxy, suddenly packs up and goes rogue, drifting through cosmic neighborhoods like a wandering titan. Astronomers recently spotted these runaway behemoths, and their very existence shatters what we thought we knew about how galaxies form. These aren't your typical lurking in the shadows black holes. They're cosmic renegades barreling through space at staggering speeds, leaving scientists scrambling to explain how something so colossal could break free from its gravitational throne. Take the case of the black hole dubbed the Cosmic Bullet. Clocked racing through its galaxy at over 4 million miles per hour, it's fast enough to travel from Earth to the Moon in under 15 minutes. What could possibly launch such a monster into motion? The leading theory involves a galactic collision, a violent tango where two galaxies merge, their central black holes spiral inward, and the recoil from gravitational waves kicks one out like a stone from a slingshot. Imagine the energy required to fling an object millions of times the mass of our Sun into the void. It's like watching a skyscraper get ripped from its foundations and hurled across a city by an invisible hand. But the implications go deeper than just spectacle. These rogue black holes could be stealth architects reshaping galaxies in their wake. As they plow through clouds of gas and dust, they might trigger star formation in their paths, cosmic plows tilling the fields of space. Or worse, they could sterilize entire regions. Their gravitational might disrupting nascent solar systems before they ever get a chance to form. Some researchers even speculate they could solve a dark matter mystery. What if these unseen drifters account for some of the universe's missing mass? Their sheer numbers might help explain why galaxies rotate faster than visible matter alone should allow. Here's the real kicker: finding them is like tracking ghosts. Without the telltale glow of an accretion disk, they're nearly invisible unless they happen to disturb nearby stars or gas. Astronomers have to play detective, looking for the subtle warping of light or strange stellar movements that betray their presence. And with every new detection, the story gets stranger. One rogue black hole was caught trailing a comet-like tail of newborn stars, a glittering breadcrumb trail of its passage. Another appears to be dragging an entire cluster of smaller black holes behind it, like a mother duck with a line of ducklings. The discovery forces us to rethink the life cycle of galaxies. If black holes can be evicted from their cores, what stops entire galaxies from unraveling? Could our own Milky Way one day host a wandering colossus slipping silently through its spiral arms? The cosmos loves to humble us. Just when we think we've mapped the rules, it throws a curveball, and these runaway giants, they're not just anomalies. They're proof that the universe is far more dynamic, far more unpredictable than we ever imagined. Deep in the heart of our Milky Way, something impossible is happening. A fountain of antimatter erupting into space with enough energy to power civilizations for millennia. This isn't science fiction. It's the real head-scratching mystery of the antimatter geyser, a cosmic fire hose blasting positrons, the antimatter twins of electrons, straight out of our galaxy's core at nearly the speed of light. Imagine flipping a switch and watching water defy gravity, shooting upward endlessly. Now replace water with particles that annihilate on contact with normal matter, and you've got a phenomenon so bizarre it's kept physicists awake for decades. What makes this antimatter jet so baffling isn't just its existence, but its sheer scale. Stretching over 25,000 light-years, it's a structure so vast, if our eyes could see it, the geyser would arc across the night sky like a celestial rainbow. But here's the kicker: antimatter shouldn't exist in these quantities. According to everything we know about particle physics, the Big Bang should have created equal parts matter and antimatter, which would have annihilated each other instantly, leaving nothing. Yet here we are, and here it is, a surplus of antimatter pouring into the void like a broken cosmic faucet. So where's it coming from? One leading theory points to dark matter, the invisible glue holding galaxies together. If dark matter particles collide and annihilate, they could spawn positrons as a byproduct. It's like striking two invisible rocks together and watching sparks fly, except these sparks could rewrite the rules of physics. Another camp argues pulsars spinning neutron stars are the culprits. Their intense magnetic fields acting as particle accelerators, churning out antimatter like factories. But neither theory fully explains the geyser's intensity or its eerie symmetry. Then there's the annihilation puzzle. When positrons meet electrons, they should destroy each other in flashes of gamma rays. Yet the geyser's antimatter streams far beyond the galaxy's edge without disappearing. It's as if these particles have a secret escape route, dodging destruction in ways we can't yet model. Some researchers whisper about exotic physics, hidden dimensions, or unknown forces shepherding antimatter safely through space. Others wonder if we're seeing the aftermath of an ancient cataclysm, like a supermassive black hole's long-forgotten tantrum. The implications are staggering. If dark matter is truly behind this, it could be our first tangible clue to its nature, a smoking gun after decades of hunting shadows. Or perhaps we're witnessing something entirely new, a process that challenges our understanding of how galaxies live and die. Every new observation deepens the mystery, proving once again that the cosmos thrives on defiance. The Milky Way's antimatter fountain isn't just a curiosity, it's a dare, a challenge flung at the feet of science, waiting for someone to rise and unravel it. The night sky seems permanent, its stars fixed in familiar constellations until you discover the ones that didn't stick around. Hypervelocity stars are the universe's runaway freight trains, streaking through space so fast they're not just escaping their home galaxies, they're punching free from gravity's grip entirely. Some hit speeds over 2 million miles per hour, fast enough to cross the distance from New York to Los Angeles in under 5 seconds, but the real shocker. Astronomers keep finding them in pairs, twin stars flung into the abyss together, still locked in orbit around each other like cosmic dance partners refusing to let go. How does a star get kicked out of its galaxy? Picture a cosmic game of pinball. Supermassive black holes at galactic centers can slingshot stars to unbelievable speeds when they rip apart binary star systems, two stars orbiting each other, and fling one away while devouring the other. The math is brutal. If one star falls into the black hole's maw, the other gets ejected with enough energy to become a celestial cannonball. But here's the twist: sometimes both stars survive the encounter and get launched together, their gravitational bond unbroken. It's like watching two friends holding hands as they're thrown from a moving car, only to land light years apart, still connected. Then there's the supernova theory. When a massive star explodes, its collapsing core can become a neutron star or black hole. If the explosion isn't perfectly symmetrical, the newborn compact object might get a kick so powerful it rockets away, and if it had a companion star, that star gets towed along for the ride. Imagine a speedboat suddenly firing its engine, dragging a water skier behind it at impossible velocities. The universe, it seems, has a flair for dramatic exits. But hypervelocity stars aren't just cosmic oddities, they're celestial breadcrumbs. By tracing their paths backward, astronomers can reconstruct the hidden forces that launched them, mapping the gravitational fingerprints of black holes we can't see directly. Some of these stars even carry chemical signatures of their birthplaces, like interstellar postcards stamped with the conditions of long-vanished neighborhoods. And because they're moving so fast, they often wind up in the lonely voids between galaxies, where they might one day seed star formation in regions thought to be barren forever. The most poetic part: these stellar fugitives are proof of chaos and connection coexisting. Even as they're banished from their homes, some stars refuse to let go of each other, hurtling through the darkness side by side. It's a reminder that in a universe governed by collisions and cataclysms, some bonds, whether gravitational or something more mysterious, are simply unbreakable. Galaxies are supposed to be glittering metropolises of stars, right? Not this one. Meet Dragonfly 44, a cosmic ghost town where the streets are empty and the lights are almost entirely off. This so-called dark galaxy contains virtually no stars, just a whisper of visible matter floating in an ocean of darkness. In fact, 99.99% of its mass is pure dark matter, an invisible scaffold holding together what little gas and dust remain. If our Milky Way is a bustling New York City, Dragonfly 44 is an abandoned warehouse at its outskirts, eerily massive yet barely there. Scientists first spotted this shadowy anomaly in 2015, hidden in plain sight within the Coma cluster. At first glance, it seemed unremarkable, a faint smudge barely distinguishable from background noise. But when researchers measured how fast its few stars were moving, the truth hit them like a freight train. Those stars were whipping around at speeds that should have sent them flying into space unless something unseen, something colossal, was holding them down. The numbers didn't lie. This galaxy weighed as much as the Milky Way, but with a fraction of its starlight. It was like discovering a skyscraper made of fog, towering but transparent. Here's the paradox that keeps astronomers up at night. According to everything we know, galaxies form when dark matter's gravitational pull gathers gas, which then condenses into stars. But Dragonfly 44 defies the recipe. It scooped up enough dark matter to birth 1,000 suns, yet almost no stars flickered to life. Some theorize it's a failed galaxy, a cosmic stillbirth where gas cooled too slowly or was stripped away by violent encounters. Others wonder if dark matter isn't the gentle glue we assume, but a chaotic sculptor that can smother star formation entirely under certain conditions. Then there's the rogue possibility. What if this isn't an anomaly at all? What if the universe is littered with dark galaxies, hidden in plain sight like invisible ink on the cosmic page? Recent surveys suggest Dragonfly 44 might have siblings, entire populations of shadowy structures we've overlooked because our telescopes were tuned to hunt light, not darkness. Some could be ancient relics from the early universe, frozen in time before stars ever ignited. Others might be galactic zombies, remnants of normal galaxies gutted by collisions, their stars ripped away while their dark matter skeletons lingered. The implications ripple far beyond one spooky galaxy. If dark matter can clump into structures without triggering star birth, our maps of the cosmos are missing entire dimensions. These phantom galaxies could be the universe's dark matter laboratories, places where the mysterious stuff interacts with itself in ways we can't yet see. Or perhaps they're signposts pointing to flaws in our theories, hints that dark matter isn't quite what we've modeled for decades. What's certain is this: Dragonfly 44 is a mirror held up to our ignorance. In a universe where we've grown accustomed to cataloging stars by the billions, it whispers a humbling truth. The cosmos isn't just built from what shines, it's shaped by what hides. And every dark galaxy we uncover isn't just a curiosity. It's a question written in the language of the unseen, waiting for us to decipher it. Between the galaxies, in what we once thought were empty voids, the universe is alight with an intricate lacework of glowing gas threads so vast they stitch the cosmos together into a single, shimmering tapestry. These are the filaments of the cosmic web, the universe's hidden infrastructure, glowing faintly with the energy of primordial hydrogen heated to millions of degrees. Like ghostly highways, they stretch hundreds of millions of light years, connecting galaxy clusters in a network so precise, it mirrors the neural pathways of a brain. And here's the twist. These delicate strands aren't just illuminating empty space, they're tracing the invisible hand of dark matter, the universe's greatest architect. For decades, the cosmic web was just a theory, a mathematical prediction of how gravity would sculpt matter after the Big Bang. Scientists imagined dark matter as a scaffold, pulling gas into sprawling tendrils where galaxies would eventually form like dewdrops on a spiderweb. But spotting these filaments, that seemed impossible. How do you see something so diffuse, so faint against the blackness of space? The breakthrough came when astronomers realized the gas wasn't completely dark, it glowed. Not with the brilliance of stars, but with the soft X-ray hum of hydrogen atoms, superheated by the gravitational tug of war between galaxies. It's like discovering a city's power grid by the faint warmth of its wires, visible only through night vision goggles. One of the most stunning examples is the slingshot filament near the Pisces Cetus supercluster. Stretching over 50 million light-years, this river of hot gas is so massive it could fling entire galaxies along its currents. Observations show galaxies sliding along it like beads on a string, their motion betraying the filament's gravitational pull. But the real shock, the gas accounts for less than 10% of the filament's total mass. The rest is dark matter, an unseen spine holding the entire structure together. It's as if we've found the universe's blueprint, sketched in luminous ink but weighted by shadows. Now consider the implications. These filaments aren't just backdrops, they're active players in cosmic evolution. When galaxy clusters collide, the filaments between them act like shock absorbers, their gas compressing into ribbons of star-forming fuel. Some researchers believe they're cosmic conveyor belts, funneling fresh hydrogen into galaxies to keep their stellar factories running. Others speculate they might be the universe's recycling system, where gas stripped from one galaxy is transported along these highways to birth new ones elsewhere. But the grandest revelation lies in what these glowing threads tell us about dark matter. By mapping how filaments bend light from distant quasars, astronomers have begun weighing their dark matter content with unprecedented precision. Some filaments appear too dense, too sharply defined for our current models, hinting that dark matter might interact with itself in ways we've never accounted for. It's like discovering that the strings holding up a puppet aren't just nylon, they're vibrating with a life of their own. Every new observation peels back another layer. Recent studies even suggest filaments might harbor rogue planets or wandering black holes, ejected from galaxies and now adrift in these interstellar currents. Could they be the universe's dark freeways bustling with unseen travelers? We're only beginning to glimpse the answer. What's certain is this: the cosmic web isn't just structure. It's story written in glowing gas and shadow, a narrative of how the universe builds itself, one luminous thread at a time. Some stars don't just die, they detonate with the fury of a cosmic tantrum, leaving astronomers scrambling to rewrite the rulebook. Enter fast blue optical transients, or FBOT, the universe's most dramatic flare-ups. These explosions punch through the darkness with a brilliance that dwarfs even supernova, vanishing almost as quickly as they appear, like fireworks that burn out before you finish gasping. The first clue something was off: their color. Unlike the reddish glow of typical supernova, FBOT blaze in piercing blue light, a telltale sign of temperatures hot enough to vaporize steel in seconds. And their speed is just as shocking. While a supernova might brighten over weeks, FBOT skyrocket to peak luminosity in days, then fade into obscurity before most telescopes can swing into position. It's as if the universe flipped a switch, cranked the energy to 11, then yanked the cord. The leading suspect behind these outbursts, a magnetter's birth scream. When particularly massive stars collapse, they don't always form black holes. Sometimes their cores crunch down into neutron stars with magnetic fields so intense they could strip the data from every credit card on Earth from 1,000 light-years away. Theoretically, if such a magnetar spins fast enough, its magnetic fury could inject energy into the dying star's outer layers, triggering an explosion 10 times brighter than normal. Picture a shotgun blast where the gunpowder's replaced with a nuclear reactor, sudden, vicious, and impossibly luminous. But there's a twist in the plot. Some FBOT leave behind no neutron star at all, just silence. That's led to the failed supernova theory, where a star's core collapses directly into a black hole mid-explosion, choking off the blast before it can finish. The result, a cosmic burp, half an eruption, with the rest of the star's energy vanishing into the black hole's maw. It's like watching a fireworks factory catch fire, only for the flames to get sucked into a vortex halfway through the show. Then there's the rogue possibility. What if some FBOT aren't stellar deaths at all, but stellar resurrections? In denser regions of space, a black hole or neutron star might rip apart a wandering star, swallowing its gas while flinging the rest outward in a luminous shockwave. Think of it as celestial roadkill, a star shredded by gravity's teeth, its guts glowing briefly against the interstellar pavement. What makes F-bot truly revolutionary isn't just their violence, but their defiance. Every new detection scrambles our models, forcing physicists to add chapters to the cosmic explosion playbook. Some F-bot eject material at 99% the speed of light velocities once thought impossible for stellar debris. Others exhibit bizarre shapes with rings or jets that suggest hidden engines powering the chaos. The most infamous, nicknamed the Cow, even left an afterglow that flickered like a faulty light bulb, hinting at ongoing energy injections from an unseen source. Here's the humbling truth: these explosions might be more common than we realized. For decades, telescopes missed them because they're so brief, like catching a lightning bug's flash in a thunderstorm. Now, with robotic sky surveys scanning the heavens nightly, we're realizing F-bot might represent a whole new class of cosmic detonations, ones that operate by rules we've yet to fully grasp. Every flash, every blue-white spike in the data is another puzzle piece in understanding how stars live, die, and occasionally cheat death with a fireworks display that rewrites physics on the fly. It should have been over in seconds, the collision of two neutron stars, each so dense a teaspoon of their material weighs as much as Mount Everest. When they spiraled together in 2017, the event sent gravitational waves rippling through the cosmos, a burst of energy so powerful it warped the fabric of space-time itself. Scientists caught the aftermath in real time, a kilonova explosion forging gold and platinum in its wake, a literal cosmic alchemy. But then, years later, something impossible happened. The universe started echoing. Detectors picked up faint gravitational wave reverberations long after the merger's initial blast, ripples lingering like a bell's hum after the strike. This wasn't just noise, it was a clue. Space-time itself seemed to be ringing, its elasticity tested by the violence of the collision. Imagine dropping a pebble into a pond, then watching the water continue to shudder minutes later, as if the pond remembered the impact. That's what researchers observed, and it upended assumptions about how space-time behaves under extreme strain. Some theorize the echoes come from the newborn remnant, a hypermassive neutron star wobbling like a spinning top before collapsing into a black hole, its oscillations imprinting onto the fabric of reality. Others suggest the debris field, a swirling disk of ultra-dense matter, could be warping space-time like a stone tossed into a trampoline, creating secondary ripples. Then there's the tantalizing fringe idea. What if these echoes aren't just physics as usual? Could they be hints of exotic physics, like extra dimensions or quantum foam, microscopic structures in space-time that distort gravitational waves as they pass? It's a stretch, but not impossible. The echo's frequencies don't quite match conventional models, leaving room for speculation. Every new detection refines our understanding, turning this merger into a Rosetta Stone for decoding space-time's hidden properties. The most practical revelation: these echoes act like cosmic sonar, mapping the environment around the collision. By analyzing the delay and distortion of the waves, astronomers can infer the remnant's shape, the debris disk's density, even the neutron star's internal composition, details once thought lost the moment the initial signal faded. It's as if the universe left us breadcrumbs, a trail of vibrations whispering secrets about matter pushed beyond known limits. What's certain is this: the merger didn't just end. It left a fingerprint on space-time, a ghostly afterimage still revealing its secrets years later. And with each echo, we're reminded, the cosmos doesn't do encores unless it's trying to teach us something. Imagine stepping outside on an alien world and looking up to see the entire sky ablaze with auroras, not in delicate ribbons of green, but in overwhelming, continent-sized curtains of crimson and violet, so bright they cast shadows on the ground. These aren't hypothetical scenes from a sci-fi novel. They're real discoveries on exoplanets where auroras make Earth's northern lights look like a dim flashlight. Take the gas giant HDP 11b, for example. Orbiting dangerously close to its star, this planet gets bombarded with stellar winds so intense they generate auroras 1,000 times more powerful than anything in our solar system. The result, a permanent planet-wide light show with charged particles scorching through the atmosphere like a cosmic blowtorch, ionizing gases into glowing plasmas that would render the night sky as bright as twilight. But how do we even detect auroras on planets light years away? The trick lies in radio waves. When auroral activity ramps up, it produces distinct radio emissions, like a celestial siren only astronomers can hear. By tuning into these signals, scientists identified exoplanets like SIMP J0, 1365663 plus 0934873, a rogue world drifting alone in space, yet boasting auroras so colossal they'd be visible from neighboring star systems. The real kicker, this planet has no star. Its auroras are fueled entirely by interactions with interstellar magnetic fields, painting the sky with light in the absolute void. It's a reminder that nature doesn't need a spotlight to create spectacle, just raw, untamed physics. Now shift gears to an even more surreal atmospheric quirk, metal clouds. On worlds like WASP 121b, an ultra-hot Jupiter where temperatures exceed 2,000 degrees Celsius, aluminum and iron don't just melt. They vaporize, rising into the upper atmosphere as shimmering metallic mist. At these extremes, the planet's atmosphere behaves like a colossal foundry, with titanium and vanadium oxides swirling in gaseous rivers. When night falls, these metals condense into droplets and rain down as liquid gemstones, only to evaporate again at dawn. It's a water cycle, but forged in a nightmare furnace. Detecting these metallic skies requires a stroke of genius, spectroscopy. As starlight filters through an exoplanet's atmosphere during transit, certain wavelengths get absorbed by airborne metals, leaving chemical fingerprints in the light we capture. That's how we spotted iron vapors on Kelt 9b, a planet so hot its atmosphere is literally boiling away into space, trailing a comet-like tail of vaporized titanium. The wildest part, some of these metals might actually form solid cloud layers. Imagine skies choked with floating flecks of corundum, the mineral behind rubies and sapphires, reflecting the starlight like a disco ball made of crushed jewels. What ties these atmospheric oddities together isn't just their drama, but what they reveal about planetary diversity. Auroras teach us about magnetic fields and stellar winds, forces that could make or break habitability. Metal clouds, meanwhile, expose how temperature and chemistry dance at extremes, proving that weather systems aren't just about water and wind, but molten minerals and ionized plasmas. Together, they're cosmic test labs, pushing the boundaries of what we thought possible and whispering hints about the stranger climates we've yet to discover. After all, if a planet can have ruby rain or eternal auroras, what other atmospheric magic might be waiting in the dark? Black holes are the universe's ultimate one-way streets, or so we thought. What if some cosmic intersections don't just suck matter in, but spit it back out? Enter the white hole hypothesis, the universe's theoretical exit door, where space-time itself might reverse a black hole's rules. Imagine a fire hose blasting water instead of swallowing it, a region where matter, energy, and even causality itself emerge violently into existence, defying everything we know about gravitational inevitability. The idea isn't just speculative fiction. In 2016, astronomers tracking gamma-ray bursts stumbled upon an anomaly, an explosion dubbed GRB 060614, which flickered with rhythmic precision like a cosmic heartbeat. The pattern didn't match any known supernova or neutron star collision, but when physicists ran the numbers, one explanation fit eerily well: a white hole's birth pangs. According to the math, if a black hole's singularity were to somehow bounce at the quantum level, the resulting rebound could eject all the trapped matter in a single catastrophic burst. It's as if the universe hit undo on a black hole's feast, vomiting up everything it swallowed moments earlier. White holes aren't merely black holes running in reverse, they're cosmic paradoxes wrapped in riddles. General relativity allows for their existence mathematically. Einstein's equations work just as well for matter emerging as they do for matter vanishing. But physics abhors a one-way street. If black holes exist, shouldn't their counterparts? The problem is thermodynamics. White holes violate entropy by seemingly creating order from chaos, like a shattered glass reassembling itself midair. Some theorists argue they could only form under conditions so extreme. They'd require new physics, perhaps a loophole in quantum gravity where space-time's fabric patches itself after a black hole's death. Then there's the multiverse angle. If a black hole singularity punches through space-time, could its other end manifest as a white hole in another universe? This wormhole scenario turns white holes into cosmic fountains, spraying one universe's trash into another's treasure. Evidence might already exist. In 2019, the Event Horizon Telescope captured eerie radio echoes near Sagittarius A. Our galaxy's central black hole flares that some interpret as matter ricocheting off a hidden white hole's event horizon. But the boldest claim comes from loop quantum gravity, which suggests white holes aren't just hypothetical, they're black hole's final act. As a black hole evaporates via Hawking radiation, its shrinking core might hit a quantum tipping point, rebounding as a white hole in its last gasp. The implications: every black hole in history might eventually reincarnate as a white hole, meaning the cosmos could be littered with dormant ones waiting to erupt. Here's where things get surreal. If white holes exist, they'd be the ultimate cosmic reset buttons. A single one could repopulate a dead universe with fresh matter, seeding new big bangs. Others speculate they might explain dark energy, their outward pressure counteracting gravity's pull on cosmic scales. Or perhaps they're the source of fast radio bursts, those enigmatic blips from the void. The white hole hypothesis forces us to confront physics' biggest questions. Is time's arrow truly irreversible? Can information escape a black hole's grip? And if white holes are real, what else lurks in the equations we've yet to dare interpret? For now, they remain ghosts in the math, but as with all great mysteries, absence of proof isn't proof of absence. After all, black holes were once deemed impossible too. Picture the cosmic microwave background, the afterglow of the Big Bang, as a perfectly smooth blanket stretched across the universe. Now crumple one corner into an icy knot. That's the cold spot, a mysterious region in space chilling at nearly 70 microkelvins colder than its surroundings, spanning over 1 billion light-years. At first glance, it might seem like a statistical fluke, a cosmic typo in an otherwise uniform sky. But the odds of such a frigid anomaly forming naturally? Less than 2%. This isn't just a cold patch, it's a screaming outlier, a blister of something other. Theories to explain this cosmic frostbite range from the plausible to the mind-bending. The leading contender, a supervoid, a vast, empty bubble of space where galaxies are eerily scarce. In such a void, light climbing out would lose energy, stretching into redder, cooler wavelengths, a process called the integrated Sachs-Wolf effect. But here's the catch: even the largest known voids can't account for the cold spot's extreme chill. It's like blaming an open window for a blizzard in your living room. The math just doesn't add up. Enter the exotic possibilities. Some physicists suggest the cold spot could be a cosmic bruise, a collision with another universe during inflation, back when space-time was stretching like warm taffy. In this multiverse scenario, our universe might have bumped into a neighboring bubble, leaving behind a gravitational dent that cooled the CMB in its wake. It's the astronomical equivalent of finding a fingerprint on your window, except the fingerprint belongs to a reality you can't see or touch. Then there's the texture hypothesis, a relic defect in spacetime itself. In the universe's first fractions of a second, phase transitions like water freezing into ice might have created tangled knots of energy that later unraveled, releasing shockwaves of cold. If true, the cold spot could be a fossil of sorts, a snapshot of the cosmos's fiery infancy frozen in time, but the wildest theory, a glitch in the simulation. No, seriously, some mathematicians have calculated that if our universe were a numerical model, certain computational errors could manifest as anomalous cold regions, artifacts of limited processing power. Before you dismiss it as sci-fi, consider this. The cold spot's shape and temperature align suspiciously well with what such a glitch might produce. Coincidence? Or cosmic breadcrumb? Here's what makes the cold spot truly thrilling. It's a laboratory for extremes. Its existence challenges whether we've misjudged the universe's structure, the nature of inflation, or even the fabric of reality itself. Future telescopes like the European Space Agency's Euclid mission aim to map its galaxy distribution with unprecedented precision, hunting for voids, textures, or, well, something we haven't even named yet. Because in the end, the cold spot isn't just a scientific puzzle. It's a dare, a challenge flung at our models, whispering that the cosmos still holds cards it hasn't shown us. And whether the answer lies in parallel worlds, space-time scars, or something stranger, one thing's certain: the universe's chilliest mystery is far from frozen in time. We've seen black holes fire jets of energy before, but never like this. Meet the cosmic disco dancers, supermassive black holes blasting gamma rays in erratic, wobbling beams that flicker across the universe like a malfunctioning lighthouse. These aren't the steady streams we're used to, they're drunken cosmic fire hoses, spraying radiation in chaotic patterns that defy all expectations. The most famous offender: the black hole at the heart of galaxy Roman 3 ZW2, whose jets don't just curve, they corkscrew through space, twisting and bending as if tugged by invisible strings. So what's throwing these deadly beams off balance? One leading theory points to warped dinner plates, warped accretion disks to be precise. Normally, the superheated gas orbiting a black hole forms a flat, spinning disk like water circling a drain. But when that disk gets twisted by the black hole's insane gravity or a recent stellar snack, it can tilt at extreme angles, making the jets wobble like a top about to fall over. Picture trying to write with a pen while someone keeps nudging your elbow. That's essentially what's happening to these gamma-ray jets, their precision ruined by the unstable platform beneath them. But there's a juicier possibility: hidden dance partners. Astronomers now suspect some of these wobbling jets might belong to black hole binaries, pairs of supermassive monsters orbiting each other in tight, gravitational embraces. As they whirl around, their competing gravitational pulls could be yanking the jets back and forth, creating those bizarre corkscrew patterns. It's like watching two kids fighting over a garden hose, each tugging the stream in different directions while water sprays everywhere. The James Webb Space Telescope recently spotted tantalizing hints of this around galaxy OJ 287, where the jet's wild swaying matches computer models of dueling black holes separated by less than a light year. Here's where it gets truly bizarre. Some jets don't just wobble, they flicker on and off, vanishing for years before reigniting. Take Blazar Markarian 501, which went silent for nearly 2 decades, then suddenly roared back to life in 2017 with gamma-ray flares 1,000 times brighter than before. The best explanation: a second black hole might be periodically disrupting the jet's flow, like a child placing their hand over a sprinkler. Every time the intruder swings close in its orbit, it could temporarily block or redirect the jet, creating cosmic strobe lights visible across intergalactic space. What makes these dancing jets revolutionary isn't just their spectacle, it's what they reveal about black hole mechanics. Their wobbles act like cosmic seismographs, letting astronomers map the chaotic environments near event horizons. Some jets even display precession, a slow, gyroscopic wobble that betrays the black hole's spin rate. others show kinks and knots that might trace past mergers like growth rings in a tree. And because gamma rays travel straight through intergalactic dust, these erratic beacons give us a crystal-clear view of processes normally hidden behind cosmic veils. Most thrilling of all, this could solve a long-standing mystery: why some galaxies flicker like faulty light bulbs across millennia. If wobbling jets periodically sweep across Earth's line of sight, they'd appear to turn on and off as their beams intersect with us. It means the cosmos might be packed with black hole binaries we've missed, their presence betrayed only by their drunken gamma-ray stumbling. So the next time you see a flickering blazar, remember, you might be witnessing the universe's most destructive dance partners, locked in a gravitational tango where the disco ball is a supermassive black hole. And the light show could vaporize solar systems. At first glance at 2018, Cow seemed like just another blip in the data until it wasn't. Nicknamed the Space Cow for its random catalog designation, this explosion erupted in a distant galaxy with a brilliance that outshone entire star clusters, then vanished faster than any supernova on record. But it wasn't the brightness that baffled scientists, it was the bizarre anatomy. Most stellar explosions fade predictably, like embers cooling in a campfire. The Cow, it flickered like a strobe light, pulsing with X-rays and radio waves in erratic bursts, as if something inside was tearing its way out. And then there was the shape, an elongated, asymmetrical debris field that, when visualized, looked uncannily like a cosmic bovine caught mid-gallop. Theories erupted faster than the event itself. One camp argued for a tidal disruption event, a star ripped apart by a black hole's gravity, but the Cow's light curve didn't match. Typically, such events glow as the shredded star forms an accretion disk, heating up over weeks. The Cow's emissions, though, peaked in days, then flatlined, as if the engine powering it had abruptly stalled. This led to the failed supernova hypothesis. Maybe a massive star collapsed directly into a black hole, its outer layers rebounding in a shockwave that briefly outshone the galaxy before the newborn singularity choked off further fireworks. Imagine a bomb whose fuse burns brilliantly, then gets snuffed mid-explosion by its own collapse. Then came the wildcard idea: what if we were witnessing the birth of a magnetar? These ultramagnetic neutron stars can inject energy into their surroundings like cosmic defibrillators. If one spun to life inside the dying star, its magnetic fury might have turbocharged the explosion, accounting for the Cow's intense X-ray output. But even that didn't explain the radio emissions, which flared months later like an echo no one predicted. Some researchers proposed a fallback accretion disk, where debris from the explosion rained back onto the black hole, reigniting the system in unpredictable waves. The plot thickened when astronomers spotted a handful of similar events dubbed cow-like transients, scattered across the universe. Each shared the Cow's hallmarks: rapid rise, bizarre spectra, and lingering radio whispers. One, nicknamed the Koala, even displayed a peculiar infrared glow, hinting at dust heated by unseen radiation. Suddenly, the Cow wasn't an outlier, it was the first of a new breed. What makes these explosions revolutionary isn't just their violence, it's their defiance of categories. They're not quite supernova, not quite tidal disruptions, not quite anything in our playbooks. The Cow and its kin might represent a previously hidden phase of stellar death, one where stars die in ways we've never imagined. Or they could be signposts to phenomena we've overlooked, like intermediate mass black holes, whose unique gravity might shred stars differently than their supermassive cousins. The most tantalizing clue: a handful of Cows appear near star-forming regions where massive stars are abundant. This suggests the explosions could be linked to short-lived, hypergiant stars, celestial time bombs ticking down to detonation under conditions we've yet to model. Every new detection adds pieces to the puzzle, yet the full picture remains frustratingly out of focus. For now, the Cow stands as a cosmic Rorschach test, a splash of light begging interpretation. Whether it's a stellar autopsy, a black hole's first breath, or something entirely unimagined, one thing's clear: the universe has more ways to explode than we've dared to dream. And with each new cow-like transient, we're reminded that the cosmos reserves its most dramatic performances for those willing to question the script. Some galaxies don't just share the cosmic neighborhood, they consume it wholesale. Meet NGC 1277, the Andromeda Galaxy's monstrous cousin and one of the most voracious galactic predators ever observed. This colossal spiral isn't merely growing, it's feasting, leaving behind stellar debris trails like a cosmic crime scene. Recent deep-field observations reveal its latest victim, a smaller galaxy torn apart into a glittering stream of stars stretching over 100,000 light-years. Think of it as celestial spaghetti, the remains of a dwarf galaxy stretched into luminous filaments by relentless tidal forces. What makes this cannibalism particularly striking is the forensic detail astronomers can now uncover. Using instruments like the Subaru telescope's hyper-subprime cam, scientists don't just see the aftermath, they can reconstruct the meal itself. Chemical analysis of the devoured stars reveals they're richer in alpha elements magnesium, silicon than NGC 1277's native stars, a telltale signature of a smaller, faster-lived galaxy. It's like finding olive oil in a dish of butter noodles. The foreign ingredient betrays the cook's secret recipe. Even more chilling, the crumbs show multiple stellar populations, suggesting this isn't the galaxy's first cosmic banquet. But the real shocker lies in the timing. By modeling the debris field's dispersion, researchers realized this carnage happened shockingly recently, just a few 100 million years ago, a blink in cosmic terms. That means when dinosaurs roamed Earth, this galactic feast was still in progress. The smaller galaxy didn't go quietly either. Its core resisted longer than expected, creating visible kinks in the stellar stream where gravitational wrestling matches played out. The most unsettling part: this isn't rare behavior, it's how galaxies grow. Our own Milky Way bears the scars of past meals, like the Gaia sausage, the remains of a dwarf galaxy consumed 8 to 10 billion years ago. Even now, our galaxy's gravity is peeling stars from the Large Magellanic Cloud, creating the Magellanic Stream, a snack that'll take billions of years to digest. What sets NGC 1277 apart is its appetite. While most large galaxies absorb a neighbor every few billion years, this one appears to be in a feeding frenzy. Some suspect it's preparing for an even larger merger, perhaps with Andromeda itself. The victim's debris could be the kindling for future star formation, meaning galactic cannibalism isn't just destruction, it's recycling on the grandest scale. The ultimate irony: in 4 billion years, when Andromeda collides with the Milky Way, will become the crumbs in some future astronomer's cosmic crime scene. The universe has always run on one brutal rule: eat or be eaten. Even galaxies aren't exempt from the food chain. We think of space as an endless void, but our solar system actually floats inside a protective bubble, one that's constantly reshaping itself against the storm of interstellar winds. Meet the heliosphere, a vast, teardrop-shaped force field generated by the Sun's magnetic influence, stretching far beyond Pluto's orbit. This isn't just empty space. It's a dynamic boundary where our star's fury clashes with the galaxy's raw energy, creating an invisible shield that deflects 70% of the deadly cosmic rays hurtling toward us. Picture it like a ship plowing through an ocean. As the Sun moves through the Milky Way, it spews charged particles, the solar wind, which collide with interstellar gas, carving out a protective cavity. The heliosphere's edge isn't a hard shell, though. It's more like a porous membrane, with interstellar material seeping in while solar particles leak out. Recent measurements from NASA Voyager probes revealed something startling. This boundary ripples and folds, reacting to pressure changes like a living lung. When the Sun's activity peaks, the bubble expands, During quieter periods, it contracts, letting more galactic radiation slip through. What's truly humbling is the heliosphere's asymmetry. Data from the Interstellar Boundary Explorer IBEX shows it's not a perfect sphere but a squashed shape, with a blunt nose facing the galaxy's motion and an elongated tail trailing behind. Some astronomers compare it to a comet, its structure warped by the Milky Way's magnetic field and the uneven push of interstellar winds. But here's where it gets critical for life on Earth. Without this bubble, cosmic rays particles accelerated to near light speed by supernova and black holes would bombard our planet unchecked. These rays aren't just a radiation hazard. They could scramble DNA, mutate crops, and even influence cloud formation, altering climates. The heliosphere's magnetic turbulence scatters most of them, reducing Earth's exposure to a trickle. It's a cosmic umbrella, and we've been blissfully sheltered beneath it for billions of years. Now the plot twist: our bubble is shrinking. Over the past few decades, the solar wind's pressure has dropped by nearly 20%, letting the heliosphere contract. Some models suggest this could be part of a larger cycle, while others warn it might leave Earth more vulnerable to interstellar weather. Imagine if our cosmic shield developed holes. What happens when the next supernova shockwave or gamma ray burst rolls through? The heliosphere isn't just a curiosity, it's Earth's first line of defense in a hostile universe. And as we venture farther into space, understanding its quirks could mean the difference between survival and catastrophe. After all, every ship needs a sturdy hull, and ours is woven from nothing but solar wind and magnetism. Venus doesn't just sit quietly in our solar system, it hums. Not with a gentle whisper of a breeze, but with a deep, resonant chorus of magnetic oscillations, pulsing through its thin, toxic atmosphere like the soundtrack to a cosmic horror film. Scientists call it the singing of Venus's magnetosphere, a haunting harmonic vibration picked up by spacecraft like ESA's Venus Express. These aren't random noises, they're precise, ultra-low-frequency waves repeating in patterns so regular they could almost be mistaken for music composed by the planet itself. What makes this eerie song even stranger is Venus's lack of a global magnetic field. Unlike Earth with its protective dynamo core, Venus generates only a feeble, induced magnetosphere, a makeshift shield created when solar wind interacts with charged particles in its upper atmosphere. As these particles are whipped into motion by the sun's relentless blasts, they generate magnetic ripples that reverberate through space, producing vibrations detectable from orbit. It's like plucking a guitar string made of plasma, where the solar wind acts as the pick, and Venus's ionosphere is the trembling chord. The real shock came when researchers realized these oscillations weren't chaotic. They followed strict harmonic ratios, much like the notes in a musical scale. Some waves resonate at frequencies corresponding to Earth's Schumann resonances, the natural electromagnetic hum between our planet's surface and ionosphere. But Venus's version is darker, deeper, warped by its thick carbon dioxide atmosphere and blistering surface temperatures hot enough to melt lead. If you could hear it unprotected, it might sound like a pipe organ played in a wind tunnel, with bass notes rumbling at frequencies too low for human ears. These magnetic harmonies aren't just cosmic white noise, they're a diagnostic tool. By analyzing the song, scientists can map Venus's atmospheric density, solar wind pressure, even the planet's electrified weather systems. For example, when solar activity spikes, the pitch of the oscillations sharpens, revealing how the magnetosphere stiffens under pressure. Other fluctuations hint at unseen turbulence, like gargantuan waves breaking in the upper atmosphere, or pockets of ionized gas sloshing like water in a tilted bowl. Then there's the Parker spiral connection. Venus's magnetic waves align with the Sun's spiral-shaped magnetic field, suggesting the planet is essentially tuning itself to the solar wind's rhythm. It's a celestial feedback loop where the Sun strums and Venus echoes back a duet played across millions of miles. Some researchers compare it to sonar, with the planet's magnetosphere acting as a natural detector for invisible solar phenomena. But the most unsettling implication, Venus's song, might be a warning. By studying how its magnetic field falters under solar storms, we get a preview of what could happen if Earth's dynamo ever weakened. A magnetosphere isn't just about auroras, it's a life-preserving force field, deflecting radiation that would otherwise strip away atmospheres. Venus, with its runaway greenhouse effect and desiccated surface, shows us where that path leads. So the next time you look at Venus, that brilliant evening star, remember, it's not just shining, it's singing, a mournful metallic hymn vibrating through the void, carrying secrets about the hellscape below and perhaps a cautionary tale for worlds like ours. For decades, cosmologists faced an embarrassing gap in their cosmic inventory. Nearly half the universe's ordinary matter had vanished without a trace. Not dark matter, not exotic particles, but the regular protons and neutrons that make up stars, planets, and us. The math was undeniable. Based on the Big Bang's elemental cookbook, over 50% of the universe's expected baryonic matter was simply missing. It was like baking a cake, carefully measuring every ingredient, only to find half the flour had disappeared between the bag and the bowl. The breakthrough came when astronomers turned their gaze to the emptiest places imaginable, the voids between galaxies. Hidden in these vast cosmic deserts, they detected the faintest glow, superheated strands of ionized oxygen, woven into an invisible web stretching across the universe. These filaments, dubbed the warm-hot intergalactic medium WIM, are the universe's hidden plumbing, a labyrinth of plasma so diffuse, a single cubic meter might hold just a few lonely atoms. But multiply that by the sheer volume of intergalactic space, and suddenly the numbers add up. All that lost matter had been hiding in plain sight, simmering at temperatures between 100,000 and 10 million degrees, too hot to form stars, too faint to see directly. Here's the ingenious part: spotting something so ethereal required cosmic detective work. Researchers used distant quasars, the universe's natural flashlights, as backlights. As quasar light passed through these filaments, certain wavelengths got absorbed by oxygen atoms, leaving spectral fingerprints in the light we received. It's like holding a flashlight behind a glass of murky water. Even if the water looks clear, the patterns in the light reveal what's dissolved inside. The eureka! A moment arrived when surveys like the Hubble Space Telescope's Cosmic Origins spectrograph tallied these absorption lines across thousands of quasars, confirming the WIM existence at scales previously unimaginable. But the real surprise was the filament structure. Far from random tendrils, these plasma rivers trace the cosmic web's precise scaffolding, the same web dark matter supposedly sculpted in the early universe. That means ordinary matter, though outnumbered 5-to-1 by dark matter, still obediently clusters along these invisible gravitational contours, like iron filings aligning to a magnet's unseen field. Some filaments stretch over 500 million light-years, threading galaxy clusters together like beads on a string, their glow faint but undeniable. Now for the cosmic irony. This missing matter wasn't just hiding, it was essential all along. Those scalding plasma strands act as intergalactic fuel depots, funneling fresh gas into galaxies to birth new stars. Without them, galaxies would have exhausted their star-forming material eons ago. They're also cosmic sponges, soaking up heavy elements blasted out by supernova and redistributing them across the voids, meaning the iron in your blood likely cycled through these filaments before reaching Earth. The mystery's resolution is a lesson in humility. For years, we assumed the universe's ordinary matter would announce itself loudly in stars or gas clouds. Instead, it whispered, woven into the fabric of nothingness. It's a reminder that sometimes the grandest truths aren't found in the spotlight, but in the shadows between. And with every new quasar analyzed, we're learning that what we once called empty space is anything but. Imagine a world where the ground beneath your feet isn't rock, it's diamond. Not scattered gemstones, but continents of crystallized carbon stretching to the horizon. Meet 55 Cancri E, a planet twice Earth's size with a surface so rich in carbon, scientists estimate a third of its mass could be pure diamond. But this glittering paradise isn't just a cosmic jewelry store. It's a nightmare of extremes where the very sky rebels against the laws of chemistry, raining not water, but molten titanium and corundum. How does a planet become diamond-encrusted? It starts with the wrong kind of stardust. Most rocky planets like Earth form from silicon-rich material. But 55 Cancri E orbits a carbon-heavy star, meaning its building blocks were more like coal dust than sand. Under crushing pressures and temperatures exceeding 2000 degrees Celsius, that carbon compresses into diamond, creating a crust that sparkles with terrifying permanence. Picture cracking open the planet like a geode instead of granite or basalt. You'd find crystalline lattices hundreds of miles thick, their structure forged in a stellar crucible we can scarcely replicate on Earth. Now look up. The planet's atmosphere, what little remains, is a seething soup of vaporized metals. With surface temperatures hot enough to melt steel, elements like titanium and aluminum don't form minerals, they boil into gases, rising until they hit cooler layers and condense into liquid droplets. That's right, it rains titanium here, not in delicate drizzles but in scalding downpours that would shred any known material. Some models suggest the droplets could even solidify mid-air, creating airborne shards of metallic glass, a sandstorm with blades forged in the heart of a furnace. The real twist, 55 Cancri E might be tidally locked, meaning one side perpetually faces its star while the other drowns in eternal night. On the day side, diamonds could literally sublime, transitioning straight from solid to gas, creating diamond vapor winds that howl toward the frigid night side where they'd refreeze into carbon hail. It's a water cycle but rewritten by a mad scientist. Evaporation, condensation, and precipitation, all starring materials we consider precious and inert. What fascinates scientists isn't just the spectacle, it's how this world bends our understanding of planetary formation. Standard models struggle to explain how such carbon-rich systems develop, suggesting our solar system might be the oddball, not the norm. Even more intriguing, 55 Cancri E's extreme conditions could forge exotic carbon allotropes we've never seen. Structures harder than diamond or stranger than graphene, materials that might rewrite textbooks on chemical bonding. Yet for all its horrors, this diamond planet offers a glimpse of cosmic alchemy at its most inventive. It's proof that the universe doesn't just create worlds, it experiments with them, twisting chemistry into forms both beautiful and monstrous. And somewhere in those glittering wastelands under skies raining liquid metal, lies a truth we're only beginning to grasp. The line between jewel and hellscape is thinner than we ever imagined. Dark energy wasn't supposed to change. When astronomers first discovered the universe's expansion was accelerating, they assumed this mysterious force, whatever it was, had been constant since the dawn of time. But new data is tearing up that assumption, revealing fluctuations in dark energy's strength that could send cosmology back to the drawing board. Imagine tightening a guitar string, expecting a steady note, only for it to randomly loosen and tighten itself. That's the chaos dark energy might be introducing to cosmic history. The bombshell came from the Dark Energy Survey, a decade-long project mapping millions of galaxies. When researchers compared the universe's expansion rate at different epochs, they found a glaring discrepancy. Dark energy appears to have been weaker in the past, ramping up its push over billions of years. If confirmed, this isn't just a tweak to the models, it's a full-blown mutiny against the standard cosmological framework. The Lambda CDM model, which has guided astronomy for decades, treats dark energy as a static property of space itself, represented by Einstein's cosmological constant. But these findings suggest dark energy could be dynamic, evolving like a living thing rather than sitting idle. Here's where it gets thorny. If dark energy's strength varies, it might not be a fundamental property of space at all. Some theorists now speculate it could be a new field, similar to the Higgs field but with repulsive gravity, a cosmic anti-glue that grows stronger as the universe stretches. Others wonder if we're seeing the fingerprints of extra dimensions where gravity leaks into hidden realms, making dark energy appear to fluctuate, the wildest hypothesis. Dark energy might interact with dark matter, exchanging energy in a cosmic tug-of-war we've yet to decipher. The implications are staggering. A dynamic dark energy could rewrite the universe's fate. Instead of a big freeze where galaxies vanish over an eternal horizon, we might face a big rip, dark energy growing so dominant it tears atoms apart. Alternatively, it could wane unexpectedly, allowing gravity to regain control and collapse the cosmos in a reverse Big Bang. But the real drama lies in the data's tension. Independent measurements from quasars and supernova don't all agree, leaving astronomers in a bitter debate. Is this a systematic error, or is the universe truly more chaotic than we thought? Upcoming telescopes like the Vera Rubin Observatory aim to settle the score, but for now, one thing's clear: dark energy isn't playing by the rules, and if it can change once, who's to say it won't change again? The cosmos, it seems, still holds the ultimate trump card. Most comets put on a predictable show: a bright coma, a streaking dust tail, maybe some gas venting as they near the sun. But when 2I/Borisov came barreling into our solar system in 2019, it brought fireworks no one predicted. This interstellar visitor, only the second ever confirmed, didn't just drift through. It erupted with a cyanide gas tail so intense, telescopes could practically smell the bitter almonds from millions of miles away. And that toxic surprise, it wasn't just a curiosity. It was a postcard from another star, written in chemistry we're only beginning to decode. What made Borisov's cyanide outburst so shocking wasn't the gas itself. Comets in our solar system often contain traces of hydrogen cyanide. It was the sheer volume. As the comet warmed near the sun, it released enough cyanide to fill an Olympic swimming pool every 10 seconds, with concentrations up to 9 times higher than any local comet. For scientists, it was like biting into what you thought was a chocolate chip cookie, only to discover it was packed with chili peppers. This wasn't just a stronger version of what we knew, it was a fundamentally different recipe. Then came the real twist. Borisov's dust wasn't behaving like solar system comets either. High-resolution images from the Hubble Space Telescope revealed its grains were unusually compact and dry, more like tiny pebbles than the fluffy snowballs we're used to. That texture hints at a formation environment vastly different from our own Oort cloud, possibly a colder, harsher place where ices clung tighter to rock. Some researchers even speculate Borisov's home system might have had a violent past, with collisions or stellar flares baking its comets into these dense, arid lumps before flinging them into the void. But the grandest revelation was hiding in Borisov's water. When astronomers measured the ratio of heavy hydrogen deuterium to regular hydrogen in its ice, the numbers didn't match anything in our solar system. Water acts as a cosmic fingerprint. Its deuterium content reflects the temperature and chemistry of the nebula where it formed. Borisov's water was significantly heavier than most comets here, suggesting it was born in a protoplanetary disk with wildly different conditions. Maybe its star was cooler, or perhaps it formed farther out in its system where deuterium-rich ices could accumulate. Either way, this wasn't just a foreign visitor. It was proof that other planetary systems don't play by our rules. The implications ripple far beyond one rogue comet. If Borisov's chemistry is common in its home system, it suggests exoplanets there could have atmospheres laced with cyanide compounds, chemicals toxic to us, but potential building blocks for alien life. It also challenges the assumption that interstellar objects would resemble our own. Before Borisov, many expected visitors from other stars to be asteroids, not active comets. Now we're left wondering, are interstellar comets the norm? And if so, what does that mean for panspermia? Could life's ingredients hitch rides on these icy messengers more often than we thought? The most poetic detail, Borisov's journey was already over before we knew its secrets. By the time we decoded its chemistry, the comet was already racing back into the abyss, carrying traces of its origin system into uncharted space. We got one fleeting glimpse, a single page torn from a galactic library we'll never fully read. But that page was enough to prove something profound. Out there, in the darkness between stars, the universe isn't just making copies of our solar system. It's experimenting, improvising, cooking up celestial oddities that defy our expectations. And if Borisov is any indication, we've barely scratched the surface of what's possible. Stars are supposed to die once spectacularly, decisively, in a blaze of glory that scatters their guts across the cosmos. But one cosmic rebel didn't get the memo. Meet supernova imposter SN 2014C, a star that didn't just explode, but kept exploding like a firework with an endless supply of gunpowder. This wasn't a one-and-done supernova. It was a stellar performance with encores, a celestial Groundhog Day of self-destruction that's forcing astronomers to rethink everything they know about how stars die. When this star first erupted in 2014, scientists catalogued it as a typical Type II supernova, a massive star collapsing under its own weight before rebounding in a cataclysmic blast. But then, something impossible happened. Instead of fading into obscurity, the damn thing brightened again and again. Over the next 5 years, it flared up at least 3 more times, each outburst pumping out as much energy as our sun produces in a century. This wasn't just a star dying, it was a star refusing to die, clinging to existence with gravitational fingernails while physics textbooks burned in the background. The leading theory, a pulsational pair instability scenario where the star's core becomes so hot that it starts producing matter-antimatter pairs, destabilizing the entire structure. Instead of collapsing straight into a black hole, the core experiences violent convulsions, partial collapses followed by explosive rebounds that blast away the star's outer layers in waves. Picture a bellows in a forge, squeezing and releasing in rhythm, except each pump hurls stellar material outward at millions of miles per hour. These zombie surges could explain the repeated brightening as shockwaves from later explosions slam into debris from earlier ones, reheating the wreckage into temporary brilliance. But here's where it gets weirder. Spectra from the Hubble Space Telescope revealed this star wasn't just exploding erratically. It was shedding layers like an onion, each outburst peeling away another shell of hydrogen, helium, and even heavier elements like oxygen and nitrogen. By the final detected flare in 2019, the star had exposed layers normally buried deep in its core, as if performing a cosmic striptease for astrophysicists. This wasn't just death throes, it was a stellar autopsy in real time, offering an unprecedented peek into the guts of a dying giant. The implications ripple far beyond one stubborn star. If pulsational pair instability is real, it could explain other cosmic oddities like superluminous supernova that shine 10 times brighter than they should. Some researchers speculate this mechanism might even forge hypermassive black holes by allowing stars to partially collapse, gather more mass, then collapse again like a gravitational snowball rolling downhill. Others wonder if these zombie stars could solve the mystery of certain heavy elements' origins, their repeated explosions acting as nucleosynthesis factories for gold, platinum, and uranium. Then there's the existential question: how many supernovae have we misclassified? If stars can fake their deaths multiple times before truly dying, our census of stellar explosions might be riddled with imposters. Surveys could be missing entire populations of stars that die quietly between eruptions, only to roar back to life when we least expect it. It's like realizing some of the gravestones in a cemetery are just placeholders, their occupants not just alive but in the middle of a fireworks display. What makes SN 2014C so thrilling isn't just its defiance, it's the way it forces us to confront the messy, unpredictable nature of stellar demise. Stars, it turns out, don't always follow the script. Some go out with a bang, some whimper, and some rage against the dying of the light with a persistence that borders on cosmic spite. And as telescopes grow more vigilant, we're left wondering, how many other stellar zombies are lurking in the darkness, waiting for their turn to rise? The universe hums with trillions of planets, countless galaxies, and the raw ingredients for life scattered like cosmic confetti. Yet after decades of listening, radio telescopes straining, optical arrays scanning, even AI sifting through petabytes of noise, we've heard nothing. No signals, no signatures, no evidence that anyone else is out there. This deafening silence isn't just puzzling, it's revolutionary, forcing us to confront a haunting possibility. What if we're truly alone? Consider the numbers. There are more Earth-like worlds in our galaxy than grains of sand on every shoreline. Many orbit in Goldilocks zones, where temperatures could allow liquid water and presumably life as we know it. Some are billions of years older than Earth, offering civilizations ample time to rise, expand, and announce themselves. And yet, when we point our instruments skyward, the cosmos responds with static. It's as if we're shouting into a canyon expecting echoes, only to realize the canyon might be empty, not for lack of trying. Projects like SETI Breakthrough Listen have scanned millions of stars, hunting for technosignatures, radio pulses, laser flashes, even Dyson sphere heat patterns. The Allen Telescope Array sifts through frequencies nightly, while newer efforts search for alien megastructures or atmospheric pollution from industrial civilizations. The result, a resounding null. Even the infamous WOW signal, that tantalizing 1977 blip, remains unexplained and unrepeated, a cosmic teaser with no encore. This great silence chisels away at our assumptions. Maybe life is rarer than we thought, a fragile spark that flickers out before evolving intelligence. Perhaps advanced civilizations self-destruct, their technologies outpacing their wisdom. Or could interstellar travel be fundamentally impossible, locking societies in planetary isolation until entropy claims them? The darkest suggestion, that we're early arrivals in a young universe, destined to be the ancient ones future species whisper about. But here's the curveball: silence might not mean absence. Our searchers assume aliens communicate as we do, using radio waves or lasers. What if they've moved beyond electromagnetic signals, employing neutrino beams or quantum entanglement? Or maybe they're deliberately quiet, hiding from something or someone. The dark forest hypothesis paints a chilling picture: civilizations staying silent to avoid attracting predators, treating the cosmos like a jungle where visibility equals death. Then there's the anthropic elephant in the room. If life were abundant, we'd likely see its footprints, probes, artifacts, or stellar-scale engineering. That we don't might suggest a great filter ahead of us, some near-inevitable catastrophe that obliterates all advanced life. The filter could be behind us: abiogenesis is freakishly unlikely, or ahead: nuclear war, AI, climate collapse. Either way, the silence screams caution, yet hope flickers in unexpected places. Some argue we've barely scratched the surface, like searching a single drop in the ocean then declaring it fishless. New telescopes like the Square Kilometre Array could detect airport radar-level transmissions from dozens of light-years away. Others propose looking for stellar engines, entire stars being moved by hypothetical alien megaprojects. Even if we never hear a whisper, the search reshapes us. It forces humility, sharpens our tech, and ironically unites humanity in shared curiosity. The great silence isn't just about aliens. It's a mirror reflecting our own fragility, our narratives of significance, and the unnerving vastness of our cosmic stage. Whether we're alone, first, or simply unheard, one truth emerges: the universe owes us no answers. And that makes every signal we don't receive the most profound message of all. Those ghostly radio circles floating in the cosmic abyss aren't just strange, they're rewriting the rulebook for how structures form in the universe. When the Milky radio telescope in South Africa first mapped ORC-4 in unprecedented detail last year, it revealed bizarre substructures no one anticipated: intricate spiral arms of radio emission swirling inside the ring like galactic fingerprints, defying all known models of shockwaves or explosions. If these were simple remnants of galactic collisions, why do some display perfect symmetry while others look like shattered glass? Why do a handful show central galaxies while most float in emptiness, untethered to any visible source? One breakthrough came when astronomers cross-referenced ORC positions with new gravitational lensing surveys. The results were chilling: several circles align precisely with regions where space-time bends more sharply than visible matter can explain, as if the rings are marking portals to denser pockets of dark matter. This has sparked the dark matter annihilation hypothesis, where unseen particles collide at the edges of these invisible halos, producing bursts of radio waves as a byproduct. Imagine dark matter not as a passive scaffold, but as an active participant in cosmic light shows, its hidden interactions blazing trails we can only perceive in radio silence. Yet not all researchers are convinced. A competing faction argues the circles might be relics of extinct quasars, the dying screams of supermassive black holes that switched off millions of years ago. As these black holes' particle jets faltered, they could have left behind expanding bubbles of magnetized plasma, like smoke rings from a cosmic cigar. Supporting this, the LAFAR telescope recently detected faint X-ray shadows inside two ORCs, hinting at long-cooled jets frozen in time. But the theory stumbles when confronted with ORC-1, which displays multiple concentric rings, a structure impossible to explain with single-jet models. The plot thickens with the discovery of time-traveling ORCs. By analyzing light polarization patterns, a Caltech team found evidence that some circles' magnetic fields are aligned in ways suggesting they're far older than their host galaxies, as if the rings existed before the stars around them formed. This has birthed the radical primordial magnetic fossil theory, proposing that ORCs could be scars from the early universe's phase transitions, when the fundamental forces first separated and imprinted magnetic fields on scales we're only now learning to see. Next-generation tools are poised to crack the case. The square-kilometer array, set to fully deploy in 2028, will map ORC magnetic fields with 100-fold greater sensitivity, potentially spotting the telltale twisting patterns of black hole jets or dark matter decays. Meanwhile, NAS, a newly upgraded Chandra X-ray observatory, hunts for faint thermal halos around the rings, evidence of the blistering gas expected in galaxy merger scenarios. Even amateur astronomers are joining the hunt through distributed computing projects, sifting through radio data for overlooked ORC candidates in our galactic backyard. What makes these enigmas invaluable isn't just their mystery, it's their sheer scale. Spanning up to 10 times the Milky Way's diameter, ORCs challenge our definitions of what constitutes a single astronomical object. They force us to question whether we're seeing independent phenomena or interconnected nodes in some vast, unseen network. Every new observation peels back another layer, revealing a universe far stranger than our textbooks ever dared suggest. One where rings of radio light might be anything from dark matter's handwriting to echoes of black holes past, or perhaps something we haven't even imagined yet. Imagine a cosmic wrecking ball, a black hole with the mass of 1 billion suns, hurtling through intergalactic space at unimaginable speeds. This isn't science fiction. It's the terrifying reality of rogue supermassive black holes, and new simulations reveal they might be rewriting galactic futures in ways we never anticipated. When these gravitational titans get ejected from their host galaxies, often through violent mergers or recoil from asymmetric gravitational waves, they don't just vanish into the void. They become seeds of chaos, carving swaths of destruction that could alter the fate of entire galactic neighborhoods. Recent supercomputer models from the Harvard-Smithsonian Center for Astrophysics paint a startling picture. A rogue black hole passing through a spiral galaxy wouldn't just bend its star's paths, it could unravel the galaxy's very structure. The simulations show how the intruder's gravity creates overlapping shockwaves in the host galaxy's gas clouds, triggering bursts of star formation in some regions while quenching it in others. It's like throwing a boulder into a pond, except the ripples are made of newborn stars and collapsing nebulas, and the pond is 50,000 light-years across. One particularly striking simulation followed a rogue black hole plowing through a Milky Way-like galaxy. Within just 10 million years, a blink in cosmic time, the galaxy's elegant spiral arms were warped into chaotic tendrils, its central bulge stretched like taffy. But the real surprise lies in the black hole's long-term effects. Unlike a meteor's fleeting impact, these monsters leave gravitational scars that persist for billions of years. As they pass through galactic halos, the vast clouds of dark matter surrounding galaxies, they create density wakes, like the turbulent trail behind a speedboat. These wakes act as cosmic flypaper, redirecting streams of gas and even smaller galaxies into bizarre new orbits. Some models suggest this could explain certain orphaned globular clusters, ancient star groups that seem to float untethered between galaxies, possibly shepherded there by rogue black holes eons ago. The most dramatic scenarios involve future cosmic collisions. When two galaxies merge, their central black holes usually spiral inward and eventually coalesce. But if one galaxy already lost its black hole to an earlier ejection, the merger plays out differently. Simulations show the remaining black hole can end up oscillating wildly through the newly merged galaxy, its gravity stirring up the gas so violently that star formation shuts down entirely. This might solve the mystery of why some massive elliptical galaxies, which should theoretically be star-making factories, are instead red and dead, packed with aging stars but devoid of new ones. A rogue black hole's absence, it turns out, could be as disruptive as its presence. Yet here's the twist: not all rogue black holes are agents of destruction. Some might be galactic midwives. When one plows through a dwarf galaxy's sparse gas clouds at just the right angle, its gravity can compress the gas into dense knots capable of collapsing into stars. There's even evidence this happened in our own cosmic backyard. The ultra-faint dwarf galaxies orbiting the Milky Way show star formation spikes that align suspiciously well with predicted past encounters with stray black holes. Talk about a backhanded compliment. A gravitational monster smashing into your galaxy might be the best thing that ever happened to your star-forming prospects. The ultimate irony: these simulations suggest our own galaxy might owe its structure to ancient rogue black hole flybys. The Milky Way's outer disk shows strange warps and stellar streams that align poorly with predictions of satellite galaxy interactions. But when researchers added a passing black hole with a few million solar masses to the models, the fit became eerily precise. It's a humbling thought that some long-vanished black hole, now drifting in the void, might have nudged our cosmic home into its current shape billions of years ago, leaving no trace but the stars themselves as witness. From rogue black holes rewriting galactic histories to ghostly radio circles defying explanation, these 25 cosmic phenomena aren't just curiosities. They're breadcrumbs scattered across the universe, each one leading us deeper into the labyrinth of the unknown. Every bizarre discovery, from diamond planets to antimatter geysers, isn't an endpoint but a doorway, inviting us to question what we think we know about space, time, and the very fabric of reality. The more we uncover, the clearer it becomes. The cosmos thrives on chaos, on the unexpected, on truths stranger than our wildest hypotheses. What ties these enigmas together isn't just their shock value, it's the way they humble us. For every mystery solved, a dozen new ones emerge like fractal patterns in the dark. Take the cold spot, which could be a bruise from another universe, or orc, those ghostly rings that might be dark matter's signature. These aren't just puzzles for astronomers, they're reminders that the universe refuses to fit neatly into our models. It's as if the cosmos is winking at us, whispering, "You haven't seen anything yet." But here's the magic. These breadcrumbs aren't just for scientists in lab coats. They're for anyone who's ever looked up at the night sky and wondered. Maybe your curiosity was sparked by the idea of hypervelocity stars racing through the void, or the eerie hum of Venus's magnetosphere. Whatever it was, that spark matters, because the next breakthrough could come from a fresh pair of eyes, a new perspective, or even a comment left under a video like this one. So keep questioning, stay hungry for the unknown. Hit subscribe if you want to join us as we chase down the next cosmic headline, because the universe isn't done surprising us. And drop a comment below which of these 25 phenomena left you awestruck. Was it the rogue black holes playing pinball with galaxies, or the diamond planet where it rains molten titanium? The conversation doesn't end here, it's just getting started. After all, the greatest discoveries begin with a simple thought. What if, and in a cosmos this wild, the possibilities are infinite?